Hey everybody, so as I mentioned in last lecture, today we're going to go over the chi-square test. Brief agenda, we're going to start with the definition like always. We're going to look at the distribution like we usually do, the chi-square distribution. In this case, we've looked at t, we've looked at f, now we're going to look at chi-squared. And then we're going to do a practice problem as you requested in the feedback form. That I think you'll find really helpful, and it is a real-world scenario, even though the data is made up. That statisticians will do all the time who work in the gambling industry. So let's start with what the chi-squared test is. I put of independence here because you're kind of assuming the null hypothesis here is that there's no relationship between your data. And the idea here is we covered T and F, which were useful for quantitative response variables. You could also have a categorical variable that splits it into groups. So it covers both quantitative, like a single response variable that's quantitative, as well as the effect of a categorical variable on a quantitative variable, whereas a chi-square test is going to look at two categorical variables, so you can't apply the same techniques. And then towards the end of class, we're going to talk about regression, which covers all those scenarios. In addition, it will also cover when both your independent and dependent variables are quantitative. So it's much more flexible than these tests we've been covering. Although you will see that the t-test and the f-test are very similar to regression. They're kind of like a subset of regression. So that's a little preview of what's to come. But to summarize what's on this slide, with a chi-square test, we're looking at two categorical variables. And I want you to remember the probability rules that we've talked about. So when we assume independence, that means that the probability of an event doesn't change from knowing the outcome of the other event, right? So we had some probability rules, something like the probability of A and B equals the probability of A times the probability of B if they're independent. If they're not independent, the probability of A and B is equal to the probability of A times the probability of B given A. So it's a subtle but very important distinction, and that is kind of the assumption that we're going to make in calculating this chi-squared statistic, which you'll see when we get to the example. But yeah, the probability rules are going to be really helpful because the expected values in your table are going to make that assumption of independence to calculate that expected value. And then we're going to see how different what you actually observed is from what you expected under the assumption of independence. And I want you to take some time to think of an example of two categorical variables for which you might apply this test. I give you one here. So this is one that might be a little surprising, but there is actually a relationship between someone's political affiliation and the type of vehicle they drive. So like it's been demonstrated that people who drive hybrid cars tend to be more liberal. People who drive motorcycles tend to be white and male, which is also, that's the lurking variable that is also affiliated with political affiliation. So those are two categorical variables, right? Political affiliation takes on a range of categories, primarily Democrat, Republican, independent, and then various third parties. And then your vehicle can be, a truck, hybrid, and so forth and so on. So again, you can't apply the tests we've learned so far, and that's where this chi-squared test statistic comes in. I want you to take some time to think of another example on your own for which you might apply a chi-squared test. Okay, so let's talk about the hypotheses here. So under the null, the variables are independent. That's the assumption you're making. This is another scenario, just like the alternative hypothesis when we covered ANOVA, that you just say not H sub O and you don't need to use mathematical notation, although some of you did, and that's fine. But in this case, there's no notation here. We're just saying the variables are independent. There's no relationship between political affiliation and vehicle driven, or, as you'll see in this later example, with blackjack, the cards being drawn. Whereas the alternative is that the response variable depends on the explanatory variable. You might remember we've thrown out a lot of words here. In synonyms for response are outcome or dependent variable, and explanatory can also be called independent, or sometimes people call it the X variable. I'm trying to remember if there's anything else we referred to it as. Explanatory variable, that's what's written here. So there's a lot of synonyms for the relationship. You could think of it as Y on X, response on explanatory, outcome on explanatory, or dependent on independent. So let's start by looking at the chi-square distribution. So again, you'll see the subscript k, which is also a degrees of freedom, and you'll see the distribution depends on its degrees of freedom, right? So when k equals 1, right, it peaks much earlier on. In fact, the degrees of freedom is also the mean of the distribution. So the mean of a chi-squared 1 is 1. The mean of a chi-squared 2, which is the green distribution, is 2. And if you remember from way early in class, that's the point at which the distribution is perfectly balanced, and so forth and so on. So again, the degrees of freedom are going to be important in determining which distribution we're looking at to calculate our p-value. So let's do an actual example here. So this is a real-life scenario that statisticians who work in the gambling industry will do. Casinos have, I think if you've seen the movie 21, you're aware statisticians at one point went to casinos and made a lot of money exploiting their understanding of probability. Casinos caught on, and now statisticians work for casinos, and they have rules in place limiting people's ability to use probability to win, and they even have statisticians who work for them to identify people who violate those rules. This scenario is much more straightforward. In blackjack, you can't really use probability to your advantage. You can count cards. That's a whole separate thing. There's a separate way they catch cheating there. But in this case, the type of cheating we're investigating is through the dealer. So for people who are unfamiliar with blackjack, the most valuable cards in the game are 10, Jack, Queen, King, Ace. And the reason those cards are most valuable is because you need some combination of those cards in order to get blackjack, which pays out more than any other hand you could be dealt. Typically 150 to 200%, depending on the rules in the casino. So one way a dealer could cheat is, let's say their friend is gambling at the table, is they could somehow, with sleight of hand, give them more of those sorts of cards than they deal to themselves, because in blackjack you're playing against the dealer. So the casino is investigating a particular dealer to determine if they're cheating, and to do so, they collect data on the number of cards greater than or equal to 10, which I mentioned previously, versus the number of cards less than 10, which are less valuable because you can't make blackjack with cards less than 10. So this is their actual results of what they observe, right? And this is a really simple table. It's just 2 by 2. We're looking at how many cards the dealer gave themselves that were 10 or greater, how many cards the dealer gave the player that were 10 or greater, versus how many cards were less than 10. Right, and it just so happens I made these add up to 100 in terms of the columns, just to make the math easier. Although the rows do not, and you'll see why that's important when we calculate the chi-square. So this is the data they see, and just looking at this, I want you to do some EDA and think about, what do you think? Is there some evidence of cheating before we start looking for statistical significance? So if you remember from my brief description of blackjack, these sorts of cards are more valuable, right? And the player seems to have gotten a greater share of those types of cards than the dealer. Similarly, for the less valuable cards, the dealer got more than the player. So it's possible that cheating is going on, but we want to be certain, obviously, before making any kind of decision. So what we're going to do next is calculate the totals, because that's going to, again, using the assumption of independence, help us calculate our expected value for our chi-squared statistic. So here's our totals, right? And as I said, the columns add up to 100 just to make the math easy. And then row-wise, we have 80 and 120. This isn't always going to be the case that the columns add up to the same number. Even in blackjack, this is very unlikely the case because sometimes a player will be dealt more cards than a dealer and vice versa. I just did this to make the math easy for this example. So how do we calculate our expected results? Well, what we're going to do, it's very intuitive. Under the assumption of independence, you could probably figure out how to do this without me giving you the formula. So just looking at this table, if the dealer and player are indeed independent, right, I need the probabilities of receiving 10 or more to be equal for the dealer and for the player. And the way you could do that is using these totals. We know that the proportion of 10 plus overall is 80 out of 200, which simplifies to 40%. And that's in fact what you get because it's out of 100, so you get 40 for the 10 plus, and then 120 out of 200 is 60%, and you get 60 for each. You could think about it intuitively, or if for those of you who like the formula, it's very simple. It's row total times column total divided by grand total. And so that varies for each cell. So for example, for this cell here, let's start with the first cell, right? The row total times the column total. The order doesn't matter. You just do row times column because multiplication is commutative. You're going to get 800, and then you're going to divide by the grand total, 200, and you'll get that 40. Similarly, if we want to do this cell here, we look at its row total, which is 120, its column total, which is 100, we get 1,200, or 12,000 rather, and divide by 200, and we get 60, right? So again, and the formulas do repeat because the row totals, the row total will change depending on what row you're in, but we did both rows, and the column totals don't. So you're going to get the same formulas there. But this is a good, simple formula to remember for those of you who want another way to get the expectations without relying on like this concept of independence and having to think through if these were independent, what would my expectations be? So now we have our expected values and our actual observed values. So to calculate our F statistic is pretty straightforward. I'm going to go back a few slides actually. And I'm sorry, I said F statistic, I meant chi-squared statistic. Our chi-squared statistic is simply our observed minus our expected. We square it, like always, to get rid of the negatives and positives. And then we divide by the expected. And that's a sort of normalization that's going on when we divide by expected. And then we sum them all up for each cell in the table. Now the reason I highlighted these in green is this is a really good sanity check that you did your expected table correctly, because your totals shouldn't change when you're doing your expected results. Again, whether you use this formula or you use the intuition behind independence that we talked about before, these totals should remain the same. So this is a good sanity check, and that's why I wanted to highlight that in green and draw your attention. So now let's calculate the actual chi-squared statistic. So this is my observed. I'm going to subtract my expected, 35 minus 40. I'm going to square it, and then I'm going to divide by my expected. And that's the first term in my chi-squared statistic. And I do this for every cell in the table. So my next one would be 45 minus 40. That difference squared divided by 40, and so forth and so on. And you can, I just used an ellipses here instead of doing all of them, but you see the last one is 55 minus 60 squared divided by my expectation, which is 60. And you can see that the numerator is in fact always going to be 25, right? Because I have the difference here is 5, the difference here is 5, the difference here is 5, the difference for this cell is 5. So it's always going to be 25. So I'm going to have 25 over 40 plus 25 over 40 plus 25 over 60 plus 25 over 60, which is just 50 over 40 plus 50 over 60. And if you do that math out, you're going to get this decimal. So that's our chi-squared statistic. Now we have to convert that into a p-value, and I do that in R. You could use whatever language you like, including JUMP. They're all going to take the same input, though, which is the statistic, the degrees of freedom, and then whether you want the right tail or the left tail. They're all languages require those three parameters in order to convert your statistic to a p-value. So how did I calculate the degrees of freedom? This is the formula right here. It's the number of rows minus 1. There's an S missing here, but it's the number of rows minus 1 times the number of columns minus 1. That's my degrees of freedom for a chi-squared. In this case, it's really simple because there's only 2 rows and 2 columns. You ignore the totals when calculating the number of rows and columns for obvious reasons. So we do our statistic, our degrees of freedom, and then in R, it phrases it as lower tail is equal to true if you want the left side and false if you want the right side. But in other languages, you'll see it as right or upper, and you just specify which side of the distribution you want. And we get a p-value of 0.14, 8, 9, and so on. So based on this p-value, would you reject or accept the null hypothesis? Hopefully most of you realize, right, the traditional alpha level type 1 error that we use is 0.05, and in this case, we're going to fail to reject. We never really accept the null. That was a little bit of a trick question. We just say we failed to reject it. We don't have evidence that it's not true. A statistician will rarely use the word accept in context of the null hypothesis. So we do fail to reject the null in this case. So how does this align with our sanity checks? Well, if we go back to the table, we did notice a difference, right? There's some indication that the player is getting better cards than the dealer. And this seems like a contradiction based on the outcome of the test, but our p-value is essentially 15%. So our alpha is 0.05 because we want to be more confident before reaching a decision, but 0.15 isn't extremely far off, right? It's getting closer to our rejection region, and that's kind of what we see in this table, right? They're not quite equal in terms of expectation versus observed, but it's also not a huge difference. They're just deviating by 5. Out of over 200 cards dealt. So I wanted to use this example to kind of convey the point that, there's what you see in your EDA isn't necessarily what you're going to reach in your conclusion, because your conclusion is also accounting for the amount of deviation and whether that is due to randomness or your null hypothesis being incorrect, your assumption behind your null being incorrect. And, if you draw cards 200 times and you deviate by 5 from the expectation, that's not overwhelming evidence that there's a kind of bias or cheating going on. But you do have some evidence, right? The way you interpret this p-value is the probability of getting this data, or more extreme being like 46 and 34, 47 and 33, so forth and so on, is about 15%. So you can still use the p-value to make sure that to sanity check what you found in EDA, but it's not always going to be as clear cut as like, well, EDA has some indication, so I'm going to reject, right? In this case, there is some indication, right? Only 15% or more sets of data would be as this extremer as extreme or more than we found in our data. However, it's still not enough to reject the null. All right, so that's an example of the chi-squared test. I think it's pretty straightforward. I think in the quiz we're going to cover the distinction between the types of tests as well as an example using chi-squared. I'm looking forward to going through those things with you next week.